let's see. Last time, I was telling you about the geometric representation of a Coxeter group, right? So let me remind you what we did, and let me talk about it. I want to make this very concrete today in this example of the dihedral group D5. And this is the group whose Coxeter diagram looks like this. Okay. So I said that in general, what I wanted to do is I started with a Coxeter group. I call the set of generators S1 up to Sn. And then what I did is that I built a vector space a real vector space with a basis alpha 1 up to alpha n. Okay. And then I put an inner product, a bilinear form, that I defined alpha I and alpha j to be equal to minus cosine of pi over mij. Okay. And I told you that for a general Coxeter group, you cannot necessarily realize this with Euclidean geometry. So you cannot assume that this right here is the usual Euclidean inner product. But actually, one thing that I didn't say and that I should say is that in most of the examples that people care about the most, and that we will care about the most, you can actually do this in Euclidean geometry. Okay? And so I want to show you how to do it in Euclidean geometry for example, for the dihedral group D5, and the same thing will work for any dihedral group. Okay? So this is just the Euclidean plane R2. Okay? And now I want to choose alpha 1 to be this vector and alpha 2 to be this vector. Okay, where this is the angle between them is pi minus pi fifths. Okay, so 4 pi fifths. So, and these are unit vectors. So then if you remember that the inner product of alpha 1 and alpha 2 is given by the length of alpha 1 times the length of alpha 2 times the cosine of the angle between them, then you find that the length of alpha 1 is 1, the length of alpha 2 is 1, and the cosine is cosine of pi minus pi fifths. And that's the same thing as minus cosine of pi fifths. Okay? And so I can actually realize this setup in Euclidean space by saying V is going to be just the Euclidean space. The basis is not the orthonormal basis that we normally take. It's this basis where the angle between alpha 1 and alpha 2 is pi minus pi over 5. And then the bilinear form is just the Euclidean inner product. Okay? So now what did I say? Basically, I said that I could make these, for each one of these guys, I would make a reflection. Which was a linear transformation of this vector space. Okay. And basically I said that the group generated by these guys I was going to think of as the geometric representation of W. This is the group generated by sigma 1 up to sigma n. Okay. Now in general, sigma I is defined to be this operation. Well, it's given by that formula, right? V minus 2 times the inner product of V and alpha I times alpha I. But I told you that if this actually was Euclidean geometry, then you can just think of this as reflection. Okay? And so in this picture, sigma 1 and sigma 2 are just going to be reflection across the lines orthogonal to alpha 1 and alpha 2. Okay? And so that's what I have drawn here. This is sigma 1. Sigma 1 is reflection across this line, and sigma 2 is reflection across this line, where they're the lines perpendicular to alpha 1 and alpha 2. Okay? And this picture you can realize very nicely if you draw a tengon, which is what I have done here, a regular tengon. Okay? Now, I would like to make a definition. So let me just say sigma. Let me move this over here. Reflections in GLV that form the geometric representation. And I want to do the following thing now. What I want to do is now think that basically I have these vectors alpha I, which live in V, and I have these geometric operations on V. And so what I would like to do now is basically apply all of these geometric operations to my roots. Okay? So what I'm going to do is that I'm going to start taking each one of my roots and just reflecting it across all the mirrors in every possible way. Okay? So for example, well, so let me so we say W acts on V, and so, well, W acts on V, meaning that each element of the group you can think of as being a linear action on V. Okay? And so I'm going to let it act on the roots, and I'm going to define the root system be basically what happens when you let all of your group elements act on all of your alpha i's. Okay? So they are the things of the form W alpha I, where W is an element of my group, and alpha I is one of the basis vectors. This is a very important definition. And to make sure that you understand it, let's actually go ahead and do that in this example. Okay? So what I'm saying is you're going to take alpha 1 and alpha 2 and just start operating by all the group elements. Okay? But we know that the group is generated by sigma 1 and sigma 2, and so what I'm going to do is basically just apply sigma 1 and sigma 2 in all possible ways to alpha 1 and alpha 2 successively. For example, what happens when I apply sigma 2 to alpha 1? Well, you see alpha 1 gets reflected across this line and lands right here. So I call this guy sigma 2 of alpha 1. Does that make sense? But I don't stop there. Then I reflect him also. Okay? What happens when I reflect him across sigma 2? Well, across sigma 2, I'm just going to go back here. Okay? Which is good because sigma 2 squared is the identity in the group. So I should go back to where it started. But for example, I could reflect across sigma 1, and that'll give me something different. It'll give me this point right here. So then I call this guy sigma 1. Actually, let me just change the notation and because I really want to think that it's the group that is acting here. So instead of calling sigma 2 alpha 1, let me call this S2 of alpha 1. So I'm imagining that the group element S2 is doing something to alpha 1, making it land here. Now I apply S1 to this, and it lands over here. And I think basically that the group element S1, S2 is doing something to alpha 1, and it makes it land there. So for example, what's the name of this guy? So it's the reflection of this one across sigma 2. So I can call it S2, S1, S2, alpha 1. But let me ask you, can I give it a different name? Well, for one thing, because in my group S2, S1, S2 is equal to S1, S2, S1, it better happen that if I do the operations in that order, I get the same point. If I reflect across S1, then across S2, then across S1, I better land here. And I will, so you can check that if you do the operations in this order, you will get the same point. And we basically proved this last time because we proved the relation sigma 2, sigma 1, sigma 2 equals sigma 1, sigma 2, sigma 1. We proved it last time. Okay. Is there a different name that I can give to this? Well, there is, because I can also say this is the reflection of alpha 2 across sigma 1. And so I could also call this S1 of alpha 2. Okay. I take alpha 2 and I operate on sigma 1, and it lands at this point. And I keep doing this. So you see, for example, this point is going to be S1 alpha 1. You see the pattern, right? No?
Looking at it, I believe it looks that way.
S1, S2, S1. No. Well, why would it be the same? Because this is 5. This is not 3. Yeah, you worried me for a second. No, S2, S1, S2, and S1, S2, S1 are different group elements in D5. So these two shouldn't be the same things. They might be if we're unlucky, but there's no reason why they should be, and as you observed, they're not in this case. So this is not an equality. I got scared for a second. Thought my whole class was going to... No.
Yeah, you thought the group entirely.
And so you keep doing this, okay? So, I don't know. This is S1 alpha 1, and you just do this in every possible way, but I think it should sound plausible to you that when you do this in every possible way, even though I can do this infinitely many times, you see that you're never going to leave this regular tangon. Because basically these reflections are both symmetries of the tangon. So then the root system consists of these 10 roots and nothing else. Okay? And this is what root systems look like. Sometimes they're an infinite mess. Sometimes they're nice and finite. Now we call the elements of 5 roots. And we call the alpha i's simple roots. Okay? Now, notice something, that alpha 1 up to alpha n is supposed to be a basis, right? And so what that means is that you can write any one of these roots as a combination of alpha 1 and alpha 2. Okay? And so I'm going to say that a root is positive if I can write it as a positive combination of the simple roots. Okay. And, of course, I'm going to call it negative if I can write it as a negative combination of simple roots. Okay? Do you like that definition? Does that seem a little strange to you? I mean, I guess the definition is fine, but it raises an obvious question, which is kind of like the question of open and closed in topology. So if you've taken topology, you know that there's something that's open, something that's closed, but these notions are not like doors that are either open or closed. Things can be open and closed, or things can be neither open nor closed. Well, this raises the same question, because can a root be positive and negative at the same time? Well, that can't be because these guys are a basis, right? So alpha can be written uniquely in this way, and that expression cannot be positive and negative at the same time. But it could be that a root is neither positive nor negative, right? It could be that when you write it in terms of the alpha i's, you get some positive coefficients, some negative coefficients. So let's look at this example right here. Which ones are positive roots out of these 10 guys? Well, basically, here's alpha 1, here's alpha 2. They're kind of looking like this. And then the positive combinations are everything in this cone right here. Right? So the positive guys are all the roots that you can find in this cone. And so basically, they are this one, this one, this one, this one, and this one. These are the positive roots. So up here is positive roots. Which ones are the negative roots? Well, you see that this is negative alpha 1, and this is negative alpha 2. The negative combinations of alpha 1 and alpha 2 are the positive combinations of minus alpha 1 and minus alpha 2. So they are the ones that are over here. And you see that all the other ones there are there. Yeah? So this one's negative, 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 negative. Yeah? So at least in this example, roots are either positive or negative. Okay? And by the way, so if it's positive, we write that alpha is bigger than 0. And if it's negative, we write that alpha is less than 0. Okay? And what I'm going to show next is that actually this is a fact for any Coxeter group. That for any root system, the roots are separated into the positive ones and the negative ones. So the fact the roots are either positive or negative, and there's no overlap between them. Okay? That's what this little dot signifies. It signifies that this is a disjoint union. Every root is positive or negative, but not both. Okay? How am I going to prove this statement? I'm going to prove it in the following way. The thing is that, I mean, if you like geometry, you're very happy that we're doing a lot of geometry today. But at some point, we're going to have to translate to algebra, right? And so this statement that I'm going to make is going to provide a translation between the geometric properties of this picture and the algebraic properties of Coxeter groups. And the theorem is the following. It says that if you take some arbitrary element of the Coxeter group, and if you take some arbitrary generator, I'm going to tell you whether W alpha I is positive or negative. Okay. So I claim that W sends alpha I to a positive root if and only if multiplying W by the generator Si makes it longer. Okay. And on the other hand, if when you multiply W by Si, you become shorter, then your elements W sends alpha I to a negative root. This is if and only if. Because we know that for any Si, multiplication by Si either makes you bigger or smaller. That makes you either positive or negative. Okay? Now you see that this theorem implies this statement because the roots are precisely the things of this form, W acting on a simple root. And so this criterion tells you exactly when you get a positive thing, exactly when you get a negative thing. And the answer is incredibly nice. It just tells you that these are equivalent to these properties that we know are very important in Coxeter groups. Okay. So, for example, let's go over here and let's try to figure out, I don't know, let's take some group element. I don't know, who wants to tell me a group element here? Someone. S1, S2, S1, S2. And let's say that alpha, let's apply this to, I don't know, S1. So we would like to know whether W alpha 1 is positive or negative. So let's check it in both ways. So first of all, what is it? Well, let's do it geometrically. Where is S1, S2, S1, S2 of alpha 1? Well, basically, I have to take S2, S1, S2 of alpha 1, and then I have to reflect that across sigma 1, and I end up right here. So I find that this is equal to alpha 2, which is positive. Okay. So that's the geometric statement. What's the combinatorial or the algebraic statement? It says that if you take W and you multiply it by S1, you become what? You become longer. And why do you become longer? Because this thing has length 4. When you multiply by S1, it has length 5. Because remember that this M is equal to 5. Okay. So this is a beautiful statement that tells you that the geometry of this picture very much reflects the length function of the Coxeter group. Okay. Any questions about it? So what I have drawn here is an even bigger example of the same thing. And I want to, as a warm-up for proving this theorem, I want us to convince ourselves that this theorem is true at least for dihedral groups. Okay. So let's see what it says for now the dihedral group of, I don't know, how many is this? I said this was an 18 gon, and so this is 9. Okay. So the angle between alpha 1 and alpha 2 is pi over 9, or rather pi minus pi over 9. Here's alpha 1. Here's alpha 2. Okay? Now, where are my reflections? Well, they're basically perpendicular to this. So here's one of them. And this is the true test of whether this is a good picture or not. Because the reflections should really be like bisectors of some of these arcs right here. So it'll make it a little crooked, and life will be okay. So there's what S1 does. It reflects across here, and S2 reflects like this. Actually, let me ask you a question. So when you learn English, the hardest thing about English is prepositions. So what's the preposition after reflect? Does it reflect across?
That's what I use.
Through?
Over.
Across. See, it's hard. Anything. So reflect over, reflect across.
Many people use in, but that doesn't come out very nice.
Okay.
That's a translation from German.
I guess I'll keep saying reflect across then. It seems different if you're reflecting across a hyperplane or across a point. It seems like they should deserve different prepositions. But anyway, I'm reflecting across hyperplanes, so I'm going to reflect across. So basically, let's see what happens when we reflect alpha 1 everywhere. Okay. For example, where's S2 of alpha 1? We have to look at this picture carefully, and you'll see that it lands right here. S2 alpha 1. Then let me reflect across S1. So where does that land? It lands right here. S1, S2, alpha 1. Basically, I want to see the pattern of what is happening here. Now let's reflect across S2. I shouldn't reflect across S1 because that's just going to bring me back, right? So reflect across S2, and I'm going to land right here. S2, S1, S2, alpha 1. And so I seem to see a pattern here that I'm kind of skipping over one of these guys. Let me just make a shorthand and say that this is the first reflection, the second reflection, the third reflection, then the fourth one is going to land here. Is that right? Yeah. Then the fifth one is going to land here, then here, and then here. And so the pattern is that you're kind of alternating 1, 2, 3, and until you get to the middle. Then you go 1, 1, and then you start going back down. So that's what happens when I reflect things that end in S2. Okay? And these are the positive roots. You see all of them. So the positive roots are the ones of the form S2, S1, S2, something like this. Okay? Which is a good thing, because what my theorem is saying is that these should be positive, because if I were to put S1 here, I would get a longer word. Right? And it should be that if I end in S1, if I try to multiply, if I try to see what an element of this form does to alpha 1, well, if I were to put an S1 here, that would make me shorter, which means that I should expect this to be negative. So let's see if that's the case. Where is S1 alpha 1? Here's alpha 1, and S1 is reflection across the vertical guy, so this is S1 alpha 1. Where's S2 S1 alpha 1? It's this one. Then S1 S2 S1 ends up over here, and you see that the same pattern occurs, except now negatively. So maybe I can call this guy the -1 guy, the -2 guy, -3 guy, and you see the pattern. -4 lands here, -5, -6, -7, -8. And so I see it, that these are the positive roots, and they correspond exactly to, by the way, this is the 8th guy, right? This is S2, S1, S2, S1, 8 times. So those are the positive guys, and those are the negative guys. And that exactly agrees with my theorem. Okay. So this is basically a proof of the theorem for 9, for the dihedral group D9. And like I said, the nice thing is you can really do it geometrically, because we know that this situation can be realized in Euclidean space. Now I should tell you that the exact same proof works for any odd guy. The pattern is always exactly the same. 1, 2, 3, like that. And this is a fun exercise. You'll agree. I know you're going to like doing this. So do it for an even guy, and for infinity. That's the other dihedral group. Okay. But this works for any. This same argument works for any dihedral group D sub odd. Okay. Is this picture clear? Any questions about it? This is a good warm-up, but we'll see that it's not just a warm-up. Okay? We're actually going to use this in the general case. By the way, this is a homework problem. It's not just an exercise. This is one of the missing homework problems. Okay. So now that we have this warm-up case of the dihedral group, let's prove this for any Coxeter group. So let me first make a simple statement, which is that actually these two things are basically equivalent to each other, and once I manage to prove one of them, the other one is going to follow very easily. So that's the first thing I would like to show, is that the first statement implies the second statement. Okay? So let's suppose that I have the first statement. And now let's suppose that I have W and SI that satisfy the second statement. I mean, the thing is that there's always kind of this nice fact that the SIs have order 2. And so I can think of W as WSI SI. Right? And then what I have here is basically that this guy, when you multiply it by SI, becomes longer. Okay? But I'm assuming that I already proved 1. And if I already proved 1, then that means that I know what happens in this situation that multiplying by a reflection makes me longer. It means that when I take that element and I multiply by the simple root, I become positive. Okay. What should I do now? Well, you see, I can redistribute here and say this is W of SI alpha I. But I know what SI does to alpha I. Yeah, because SI is SI is the reflection across the hyperplane corresponding to alpha I. So this thing exactly becomes negative alpha I. Okay. But if W sends minus alpha I to something positive, then sends alpha I to something negative. So why can I do this? I can do this because W is a linear operation. W is a linear operation, so if it does something to minus alpha I, it sends it to some positive vector, then alpha I gets sent to the negative of this guy. It's a linear operator. Okay. And so I get this, which is what I wanted. So that proves that it's enough to show the first statement. Okay. So let's prove the second statement now. I mean, the first statement. So now take W and SI with the length of WSI is bigger than W. And I want to prove it that this means that W alpha I is positive. Okay. And as with a lot of things involving a statement like this, I'm going to prove this by induction. Okay. Let me induct on the length of W. So what's the first case? The first case is that the length of W is 0. We know if the length of W is 0, then W has to be the identity. And then what does the identity do to alpha I? Well, leaves it alone, right? By definition, this is positive, right? It's a positive combination of just a single guy. So that means that there's nothing to prove in that case. Okay. So now, let's suppose this is true for lengths less than the length of W, and let's prove it for W. Okay. Now, again, if you look at a lot of the proofs that we have done that look like this, they're very similar. We need to prove a statement for W, and what we want to do is reduce it to a lower length. Now, how do I reduce to a lower length? In a controlled way, what I always do every time is just multiply by a generator that makes me shorter. Okay? And so that's what I'm going to do. So find some generator S such that WS is shorter than W. And then what I want to do is prove the statement for W by deducing it from the statement from WS. Okay? Okay. Now, here's what I'm going to do. I have two special generators that I'm paying attention to, S and SI. Okay? And so, what I'm going to do is consider those two special generators, and I know that any subset of the generators gives me a parabolic subgroup and a parabolic quotient. And we know that they are related like this. Okay. Now let me remind you what these things are. This is the parabolic subgroup, which is the things that are generated by S and SI. And remember that these are the things that cannot end in S and S or SI. And so we said that the way you get a factorization for W is that basically you write it as far as you can, except that you can't end in S's or SI's, and then you accomplish that ending with W sub j. Okay. So from this factorization, I get something like this. Right? Where, first of all, remember that this behaves nicely under length. So we prove that the length of W is the length of W super j plus the length of W sub j. And you should also remember that we described exactly what W super j was. It was exactly the lowest element, so the shortest element in the coset WJ. Now, this is a lot of symbols, but you're very familiar with this because you did this homework problem where you took this W and you saw that if you looked at a parabolic subgroup, W sub j, then that parabolic subgroup split this into cosets. Right? And I drew a picture that looked kind of like this, where the cosets look maybe like this. Here's a coset, 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 coset. And then we said that if maybe W lives in here, that means that this is the coset W times big W sub j. And then what you saw in your picture is that each one of these cosets had a unique lowest element. And that's the element that was called W super j. And this is why I wanted you to draw this picture very carefully so that now you know what this diagram means. So if you want to factor an element of the Coxeter group, you just look for the coset that it's in and look for the lowest element in that coset. And that's the first factor. And the second factor is what you need to multiply by to get W. Okay. So I'm saying that I want to prove this statement for W, that W times alpha I is positive. And the way I'm going to do it is by factoring like this. Okay. So let's see what I'm going to do now. What I'm going to do is say, okay, well, what does W do to alpha I? I mean, I need to prove that this is positive, right? Well, W is equal to W super J times W sub J of alpha I. Okay? And to understand this, W alpha I, first I want to understand what W sub J does to alpha I. Okay? So let's think about this. W sub J of alpha I. Now, what does W sub J look like? Well, W sub J is generated by S and Si. So what I have here is something that looks like SSI, 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 alpha I. And this situation I understand fully well because that's why I did that warm-up example. Okay. This looks like something like this. And so if I want to figure out whether this is positive or negative, I just have to figure out whether this word ends in S or it ends in SI. Okay. Now, of course, I want to prove that W alpha I is positive, so what I intend to prove is that this first part is positive. And to prove that, what I need to prove is that the length of W sub J of Si is bigger than the length of W sub J. Okay? And if I prove this, then by invoking this theorem in the dihedral case, by invoking it in that example, I will get this statement. So what I need to prove now is that the length of Wj Si is bigger than the length of Wj. A Coxeter statement, a Coxeter group statement. And then what I'm going to say is this. I'm going to say that W is equal to W is equal to Wj, where the length of W is equal to the length of W super J plus the length of W sub J. Okay? Now, I want to compare the length of W sub J Si with the length of this guy. So let me add this to it. And what is this equal to? Well, this is equal to the length of WSI because if I look at WSI, then this is W super J, W sub J, Si, right? And if you look at this expression, you're going to figure out that this guy still lives in W super J, because by definition it did. And this guy is generated by S and Si, because Wj is generated by S and Si, and I'm just multiplying it by Si. So that means that this thing is the factorization of this element as something in the quotient times something in the subgroup. And because of that, the length is additive. Okay. So if I want to know whether this is bigger than this, I just have to know whether this is bigger than this. But that's my assumption. Okay. So that means that this is bigger than this, which means this, which means this. So that's the first part of the proof. First part of the proof is that I just showed that this is true. Which means that it's positive, okay? Now, again, this is just SSI of alpha I. And so all of this is taking place between alpha and alpha I. These are the only two things that can appear here. And so what I'm saying is that this is just some positive combination of alpha I and alpha. Sorry. Okay. So that's my first step. Yeah. I want to prove that W alpha I is positive. And what I got so far is that Wj alpha I is positive. Now I have to figure out what happens when I incorporate this W super j. So let's see what happens. I multiply by W super j, W sub j alpha I. And so what I get is A times W super j alpha I plus B times W super j alpha. And I want to show that this is positive. Now, A and B are positive. And so one way of proving this would be to prove that these guys are positive roots. Okay. How would I prove something like that? Well, again, the reason the way I would know something like that is by translating it into this length statement if I knew that this theorem were true. Now, do I know if this theorem is true for W super j? Well, the thing is that actually I do because I'm doing an induction proof. So I'm assuming that this statement is true for everything that's shorter than W. And so in particular, it's shorter for W super j. Okay. So by induction hypothesis, this is equivalent to checking whether this thing is true and whether this thing is true. Now, of course, if I want to use the induction hypothesis, I need to check that this is true. Right? That this guy really is shorter than this. But I'll let you think about that for a second, and you'll see that that's very simple. And basically, length of W is this plus something, and you just have to show that something is not 0. Okay? Now you look at this, and there's actually an obvious reason why these guys are true. Because if we go back to this picture, W super j is the lowest thing in this coset. Now, if I multiply by Si, that's still in this coset. Yeah, because Si is in W sub j. So Wj Si is in this coset, Wjs is in this coset, and this guy is the smallest guy in the coset. So that means since Wjsi and Wjs are in the same coset, that means that these are true. So this is true, and that completes the proof. Okay. So that proof is fairly involved, but I want to make sure that you understand what the statement says, and that's what you will need to understand for the most part. It just says that the geometric property of whether a group takes a root into a positive root or a negative root can be characterized very simply in terms of the length function, which is an algebraic characterization. Okay. Right.
I discovered something, notation. The Italians around
It's much easier to get a problem with it, because the problem with it is
1955 that I'm dealing with use, here is O, and there's P,
Maybe I'll have a
yeah.
problem.
then the symmetrically opposing point, call this P slash O.
Well, I want to go talk to a
P
friend.
over O.
Oh.
And similarly, P here and G here, this would be P over G. And it works. It's very, very nice, you know. And they did that, and I've not seen it in. I've not seen them write this in the way that it is spoken. And it took me a long while to realize that's what they're saying. P over.
That's really interesting.
So we're on lecture 21. Today will be lecture 21. Is it really lecture 21 or is it just the topic? I think it's actually lecture 21.
For this class?
Or it would be for this class too. Yeah.
I don't think it is. I think it's 20. You only know because I have to index these things every week.
So then,
Every
but
day.
you missed a class.
Yeah.
That's pretty impressive.
I guess we're almost halfway there.
That's scary.
Yeah?
Yeah, I don't like that.
Why not?
Because I don't feel like I have to work.
I don't like ends of things. Yeah. Of course, at least in this class we don't have to worry about finding- What happened to your board eraser person? Mr. Jack God.
I don't know.
He just disappeared.
It's very disappointing.
Did he tell you he was going on vacation and not to think he died or anything?
He didn't tell me this time, but I'm not going to assume that he died.